Hi, and welcome back to the AP Chemistry Flipped Classroom. And we are continuing or beginning our conversation about thermodynamics, so our final unit for the year. And we begin with entropy and with spontaneity. So when we talk about spontaneous processes, what we mean is that it is a process that occurs without outside intervention. So quick review of the first law of thermodynamics, which says that energy cannot be created nor destroyed, and that the energy of the universe is constant. So spontaneous process is one that occurs within that framework. It occurs without outside intervention. Spontaneous processes are not necessarily fast. They can be fast or they can be slow. A lot of forms of combustion are really, really fast and they're spontaneous. But the conversion of diamond to graphite is also spontaneous, and it's really, really, really slow, for which the jewelry industry is eternally grateful. College Board prefers the term thermodynamically favored because it removes confusion around that idea that spontaneous means fast. So we'll try to use the term thermodynamically favored, but I will slip up and use spontaneous occasionally. So when we talk about a thermodynamically favored process, it happens without any outside intervention. If it's thermodynamically favored in one direction, it's not necessarily favored in the reverse direction. In fact, it can't be thermodynamically favored in the reverse direction. So spontaneously, a nail is going to rust. It is not spontaneously going to unrust. But with the application of outside intervention, we can make a nail unrust. So thermodynamically favored processes can be reversed, but they won't be naturally reversed. Also, temperature matters. Something that is thermodynamically favored at one temperature may not be thermodynamically favored at another temperature. As an example, ice is going to spontaneously melt above 0 degrees Celsius, but below 0 degrees Celsius, water is going to spontaneously freeze. So that's thermodynamically favored. Thermodynamically favored requires two pieces that we're going to consider: enthalpy and entropy. So let's talk about entropy. So entropy, we use the sign S, and it's a measurement of randomness or of disorder. The driving force for a spontaneous process is an increase in the entropy of the universe, which relates to the second law of thermodynamics, which says that the entropy of the universe is always increasing. Entropy is a thermodynamic function, and it actually describes the number of possible microstates for a system, or the number of possible arrangements. Nature is always going to proceed towards the states that have the highest probability of existing. Remember, driving force for spontaneous process, that increase of entropy in the universe. So, like total energy and enthalpy, entropy is a state function. Therefore, we can calculate the change in entropy by looking at the final entropy and subtracting the initial entropy, and the path it takes does not matter. So on the molecular level, what does entropy mean? We know that temperature is a measure of the average kinetic energy of the molecules in a sample. How do we measure their entropy? So our molecules have lots of different kinds of motion. We have translational motion, where they can move from one place to another. We have vibrational motion, where they can move within the molecule. And we have rotational, which is rotation on an axis or rotation around sigma bonds. All of that motion we can envision at a particular instant in time. So like if we were to take a snapshot of those molecules, and that's what we call a microstate. So each possible configuration, each possible location of each atom, each possible rotation, each possible vibrational movement of every atom or every molecule in the system is a microstate. That means that every state has a specific number of microstates associated with it, and entropy is equal to the Boltzmann constant times the natural log of the number of microstates. We're never going to have to calculate this, but this is where this comes from. So when it comes to expressing ourselves about entropy, the best way to talk about it is the possible number of microstates, that entropy is dependent on the possible number of microstates. Therefore, as the number of microstates increases, entropy increases. As the number of potential microstates decreases, entropy decreases. So this is just turning all of that into math. So we can say that the change in S is equal to K times the natural log of the final number of microstates divided by the initial number of microstates. So the more the number of microstates increases, the more the entropy increases. Number of microstates is going to increase with increases in temperature, increases in volume, and increases in the number of independently moving molecules. So all of these are things that you have known, but we're just delving a little bit deeper into the why. So how does entropy relate to the physical state of matter? As molecules have more freedom to move, there are more possible microstates, and so entropy is going to increase. So the entropy of a gas is much, much greater than the entropy of a liquid, and the entropy of a liquid is greater than the entropy of a solid. With a gas, we have so much greater volume and so much greater freedom of movement. It is much, much greater than the entropy of a liquid or a solid. How do we calculate the entropy change in a reaction? Well, just like calculating the free energy of a reaction or calculating the enthalpy change of a reaction, we can sum the entropy of the products and subtract the sum of the entropy of the reactants. It is an extensive property, so we do need to make sure that we multiply those entropies by the number of moles. And generally speaking, the more complex a molecule is, the higher the entropy value of that molecule is going to be. Notice that there is a little bit of a difference here between the delta S and delta H calculations, because we can actually measure entropy of molecules or of systems with the enthalpy. We were always looking at a change in enthalpy. So this is not a change in the entropy of products, but just the entropy of the products. All right, so our second law of thermodynamics: in any spontaneous process, there's an increase in the entropy of the universe. And that means the entropy of the universe is always increasing. So for a given change to be spontaneous, the delta S of the universe must be positive. And as with everything in thermodynamics, the universe is the system plus the surroundings. So this is actually the basis for our delta G calculation, our free energy calculation that we'll be coming to soon. Okay, so let's just do a couple of quick practice problems. So this is from one of our practice exams. And the question says, the process of dissolution of sodium chloride in water is represented in the diagram above. Which of the following summarizes the signs of delta H and delta S for each part of the dissolution process? So we know that breaking solvent to solvent interactions, breaking those attractive forces between the water molecules, is going to require energy. But we're pulling the molecules farther away from each other, and so that is also going to increase the entropy. And breaking the solute to solute interactions, again, is going to require energy, but it's going to also increase entropy. And when we form those solute to solvent interactions, so those attractive forces between the water and the ions, That's going to be a negative delta H because that's going to be exothermic. We're giving away energy when we form those attractions. But it's also going to make it slightly more ordered. And so we're going to have a negative delta S. So we're looking for positive, 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 negative, negative. So A would be our answer here. Okay. We have another example problem here. We have a sample of ice being heated to liquid water and then to water vapor, and we see the heating curve. And it asks us which lists the signs for the changes in enthalpy and entropy for the process corresponding to segment X, going from left to right. And I think this is segment X here. So we know that during this process, we're going from a liquid to a gas. So we know that entropy is increasing. So that's going to be a positive entropy. We also know that we're heating it. And so we are putting energy in. So that is an endothermic process. So it's going to be a positive delta H. And so B is our answer here. Okay. As always, I hope this was helpful. I look forward to hearing your questions in class, and I'll see you soon.